If the poles are right, this class will get popular with the next one. And we'll see.
You definitely gonna do philosophy.
Philosophy. We'll see. So I'll take those polls into account. We'll have a day where I have people come and actually vote, see if people are actually willing to show up. I'm mostly using that as a gauge to help me guess what's going to be next so I can start preparing. So we'll see how it goes. But yes, I would guess that philosophy is going to be the next one.
Okay.
All right. I think I started this.
Yeah.
Yeah. All right. So let's pick up with what we were talking about last time. So what was the last section on? What's the topological property we were talking about?
Connectedness.
Connectedness. Roughly speaking, what does it mean for a topological space to be connected?
It means that you can't find a separation on it.
Yeah, you can't find a separation on it. You can't split it into two open sets where those open sets have no overlap, neither of them are empty, etc.
Yeah.
So that's what it meant to be connected. Don't let me accidentally say compact. Compact is the next section. I might accidentally say compact. Connected. We're talking about connectedness. And then we ended last time with me introducing to you a very famous theorem from calculus called the intermediate value theorem. What does the intermediate value theorem say? Here's directly what it says from calculus. We'll read it, we'll get the pictures for it, and then we'll go over it again. So let f be a function from the closed interval ab. So these are all the numbers from a to b, including a and b. So this might be from 0 to 2 or something like that. But it's definitely a closed interval of real numbers. So let f be a function from some closed interval of real numbers to the real numbers. Let it be continuous, and let c be any point in the real numbers such that c lies between f of a and f of b. So what's f of a? It's whatever a maps to, some real number. What's f of b? It's whatever b maps to, some real number. Then there must exist some point in our domain, some x naught in our domain, such that f of x naught is equal to c, such that when we run x naught to our function, it spits out c. Let's look at this pictorially. So here in black, I have some random function f drawn. Here's some random function. Here's some random closed interval on the real number lines, a to b. When I run a through my function, it gives me f of a. When I run b through my function, it gives me f of b. What this theorem is saying is now pick any number between a and b you want, call it c. So pick any number between them that you want, call it c. Then there had to have been some point in our domain between a and b, call it x naught, such that x naught mapped to c. So if our function is continuous, then it had to, and it spits out f of a and it spits out f of b, then it also has to spit out every number between f of a and f of b. Intuitively, otherwise our function would have a hole in it somewhere between a and b, and so it wouldn't be continuous. So if it spits out f of a and it spits out f of b, it has to eventually spit out every number between f of a and f of b. Let's pictorially see why it has to be the case. Imagine that you could find some c between f of a and f of b that this function didn't spit out. So when we ran it backwards through the function, it didn't map to anything. So there would have had to have been a hole right there, a little hole, which would mean our function is no longer continuous. Remember, our calculus version of continuous is roughly, can I draw it without picking up my marker? That's continuous. If there's a little hole there, I'd have to pick up my marker to skip over the hole.
Remind me how we manage, like, let's say there's a hump, and you're only measuring the beginning of the hump and the end of the hump. Theoretically, if the C was at the top of the hump, it would be outside the range.
Okay, so let's try and come up with a more messy case. So we've got something where f of a comes up, we got some weird bump like this, something like that, right?
Yes.
Okay, once again, pick any number between f of a and f of b you want. Call it c.
Okay, the number at the very bottom of the lowest hump.
The bottom of this hump?
Yep.
That's not between f of a and f of b.
Oh, I see.
So pick any number between f of a and f of b you want, call it c, run it backwards through the function. There must have been at least one point, x naught, that mapped to it. Maybe multiple points spit out c as their value, but there must be at least one.
I see what you're saying now.
Okay, so that is the calculus version of the intermediate value theorem. Let's look at a quick corollary of that. The quick corollary of that is if you have f is a continuous function from some closed interval a, b to r, where f of a and f of b have opposite signs, in other words, f of a is negative and f of b is positive, or f of a is positive and f of b is negative. So if they have opposite signs, then there must exist some point in our domain such that the value at that point is 0. This is just a quick corollary of this. So here's our picture. F of a and f of b have opposite signs. One's positive, one's negative. 0 is a value in between them. There has to be some point in our domain that maps to 0. And in this case, the point is right here at x naught. It's wherever it crosses the x-axis. If your function's continuous and it's negative over here and positive over here, it had to cross the x-axis somewhere, is essentially what that's saying. Those two make sense? Okay. Hopefully what makes sense is how this immediately follows from this. This is just a special case of this. Because we're going to prove this. Not going to bother proving this. We're kind of going to prove this. Show you now exactly what we're going to prove. We're going to do the topological version of the intermediate value theorem. It's more general than calculus. Calculus is just a special case of topology. All right, so let f from x to r, notice that we're no longer on a closed bounded interval. Let f from x to r be continuous. Let x be connected. And let a and b be any 2 points in x such that f of a is less than f of b.
Is x a topology or just a set?
X is some topological space, some connected topological space. Okay. Remember, continuity makes 0 sense unless it's from a topological space to a topological space.
Right. Okay.
So it's understood that when I'm saying it's a function to r, we're also endowing r with the standard topology. Okay. Good. So let x be connected, let a and b be 2 points in x such that f of a is less than f of b, and let c be any point between f of a and f of b. Then there must exist some value in our domain such that it maps to c. So notice that this and this are saying identical things. The only difference is I'm replacing AB here with X, where X is any connected set. Here is a connected set in the real numbers. We can replace it with any connected set, with any topology, and the theorem still holds. So this is just a special case of this when we replace the X with the closed interval AB. Okay, so we're going to prove this. This immediately follows from this, and this immediately follows from this. So we won't bother proving these two once we prove this.
Okay.
All right, so let's get started. So let f from x to r be continuous, let x be connected, and let a and b be points in x such that f of a is less than f of b, and let c be some point between. So here's what we started with. We're trying to show this. I'm trying to find some x naught in our domain such that it maps to C. So I'm looking for a point in our domain that maps to C. That's our whole goal. Now note, if C is equal to f of A, or C is equal to f of B, then we're done. If C is equal to f of A, then A is the point that maps to C. If C is equal to f of B, then B is the point that maps to C. So, A and B are already points in our domain. We're just looking for a point in our domain that maps to C. Okay. So if C is equal to f of A, we're done. If C is equal to f of B, we're done. So let's say that C isn't equal to f of A or f of B. So if C is not equal to f of A, and C is not equal to f of B, but it's in the closed interval from f of A to f of B, what do we know about C?
It has to be less than B and greater.
It has to be less than f of B and greater than f of A. So then C is between f of A and f of B. Not equal to either of them, somewhere in between. Okay. Now we're going to assume, by way of contradiction, that there is no x naught in our domain such that it maps to C. Let's assume that nothing maps to C, and we're going to get a contradiction. What's our contradiction going to be? It's going to be that X is not a connected set. But we know X is connected. That's going to be our contradiction. So this assumption is going to lead me to the conclusion that X is not connected. I'm going to come up with the separation on X. Okay. So, assume by way of contradiction that there is no X naught in X such that it maps to C. So we're assuming nothing in X maps to C. That's our assumption. What does that mean? Well, then C isn't in F of big X. If I run my whole domain through my function, I don't get C. C is not one of the outputs of my function. If it was one of the outputs of my function, there would have had to have been an input that gave me that output. So, C is not in the image of our function. Which gives me that whatever the image of our function is, remember our function maps from X to R. It maps to real numbers. So whatever F maps to, it doesn't map to C. So whatever F maps to, it's a subset of negative infinity to C union together with C to infinity. I already knew that this was a subset of the real numbers. If it never maps to C, then it's a subset of this thing. You with me? And it turns out that this thing is going to be our separation. This is going to be a separation of F of big X. But F of big X has to be connected because F is a continuous function. Because continuous functions preserve connectedness.
Right.
Okay, so that's what our separation is going to be. So now notice a few things. Then, since F of A is in this interval, how do I know F of A is in this interval?
Because it's less than C.
Because F of A is less than C, and this is every real number less than C.
Right.
Since F of A is in that interval, F of B is in this interval, because this is everything greater than C, and F of B is greater than C, then these two sets are a separation of F of X. F of X is a subset of those two things. Those two things are both non-empty. They at least have one point from F of X in them. And these two intervals have no overlap. So they're two disjoint, non-empty sets whose union for sure gives you at least F of X. So that's a separation on F of X, but we know F of X is connected because it's the image of a connected set, since F was continuous.
Right. So it's a contradiction.
So there's our contradiction. Therefore, our assumption that there is no, assumed by way of contradiction that there is no X not in X such that this is true, our assumption must be false. There must be one. So we're guaranteed there is one. Which one? We don't know, but there is one. Because there not being one is impossible. Good with that? Okay, let's move on to some more special cases. So let F be a function from the closed interval -1 to 1 to the closed interval -1 to 1, and let it be continuous.
Okay.
These are subspaces of R with the standard topology.
Okay.
Okay. Then, there must exist some C in our domain such that when you run it through the function, it spits out just C again. Let's get a picture of this. So I know that our function, f, its domain is -1 to 1. So it needs to take every point in this real number line and from -1 to 1 and map it to something. Now, if I do this, so let's draw some function from -1 to 1. So a potential f might look something like this. Starting here, do like that. There's a potential f. Mapping everything from -1 to 1 to some subset of -1 to 1. Maybe all, maybe not. Now this line right here, this is the line y equals x, right?
Right.
This is the line where your x and y coordinate are the same, where your input and output are the same. So if this function intersects that blue dotted line, the point where it intersects it, whatever that point is the point where its input is equal to its output. So the only way that this theorem could be false is if it would be possible for me to draw some continuous function where my output has to stay between -1 and 1, and I have to map all of -1 to 1. And so I can pick somewhere to start, and I gotta stay away from the blue line. Oh no, stay away from the blue line, stay away from the blue line. I'm stuck, because I eventually have to get to 1. 1 has to map to something. And so I'll intersect it right at the top of the blue line, if I try to stay away as long as I can.
Right.
So there's a picture to give you intuition for this. Now let's actually prove it. So we define G from -1 to 1, from the closed interval -1 to 1 to R, by G of x equals f of x minus x. Notice that if G of x is 0, that means f of x equals x. Let's write that to the side really quick. If G of x is 0, then that means 0 is equal to f of x minus x. Plus x to both sides, and we get x is equal to f of x. The input is equal to the output. So I set G up so that G is a function, and it's going to be 0 exactly when f is equal to its own input. That's by construction. With me? Because ultimately I'm trying to make so I can use this lem over here. Okay. So now notice, G of -1, what is that? Here's G's definition. It's f of -1, take away -1.
0.
So G of -1, when I plug in -1 for G, I plug in -1 here, and then I plug in -1 here.
Yeah.
Negative -1 is the same thing as +1.
Right.
So G of -1 is just f of -1 plus 1, right?
Yes.
What is the smallest f of -1 can be? What is the smallest value f can spit out?
0 or
-1.
-1.
It's everything it spits out is between -1 and 1. It's sandwiched from top and bottom by these two numbers. So the smallest this part can possibly be is -1. So the smallest this whole thing can be is 0.
Right.
If f of -1 turns out to be 0, then this whole sum is 1. If f of -1 turns out to be 1/2, this whole thing is 3/2.
Right.
So the smallest this can possibly be is 0. So this value, G of -1, is always greater than or equal to 0. And similarly, what do we get when we plug 1 into this function? So plugging in 1 to G of x is the same thing as plugging in 1 for x minus 1. Plugging in 1 for all our x's. That's a 1 on I. Notice now, what is the biggest f of 1 can be?
0.
1.
Sorry.
F can spit out, the biggest value f can spit out is 1.
Right.
So the biggest this can be is 1. When I subtract 1 from it, we get 0. So the biggest G, or the biggest f of 1 can be, G of 1 can be, is 0.
Yes.
Since the biggest this can be is 1, the biggest this thing can be is 0. It can potentially be smaller, the biggest it can be is 0. So G of 1 is less than or equal to 0, and G of -1 is greater than or equal to 0. With me so far? Okay. Now let's handle the cases where G of -1 is in fact 0. If G of -1 is equal to 0, what does that mean? That means when we plug -1 in for G, we get 0. Move the -1 to the other side, and you get f of -1 is equal to, is equal to -1. Just move the 1 to the other side, subtract 1 from both sides. And so if G of -1 is equal to 0, then f of -1 is equal to -1. And we're done. That's what we were trying to show. The input is equal to the output.
Okay.
Similarly, if G of 1 is equal to 0, then here's G of 1 equals 0. Move the 1 to the other side, add 1 to both sides, and you get f of 1 equals 1. And once again, we're done, if that's the case. So now let's handle the case where G of -1 isn't 0 and G of 1 isn't 0. So if G of -1 isn't 0, it has to be greater than 0. And if G of 1 isn't 0, it has to be less than 0. So if G of -1 is greater than 0 and G of 1 is less than 0, then there must exist some point C in the domain such that G of C is 0. That's using this lemma. This is a positive number, that's a negative number.
Yes.
If you have a positive and a negative, somewhere in between you have to get 0. So then there has to exist C, I didn't specify where the C comes from, there has to exist C in the domain, -1 to 1, such that this function spits out 0 there.
Right.
But g of c equals 0 is the same thing as g of c, plugging c in for g. Here's our function g, plug in c for that. G of c equals 0. Add c to both sides, and we get f of c is equal to c. And we're done. The only one point I probably should have specified a little bit better is, notice that g here is a continuous function. How do I know it's a continuous function? F here is a continuous function. X by itself is a continuous function.
Right.
And we already showed applying arithmetic operations to continuous functions continues for it to be, enables for it to still be a continuous function. That was a while ago in the class.
Yeah.
So yes, still a continuous function. So all are logical too. All right, now let's get to the cool one. So this next theorem I told you is the one that tells us that pick any continuous function you want on the surface of a sphere. We'll use the Earth as an example. Any continuous function on the surface of the Earth you want. We are going to prove that 2 points on opposite sides of the Earth must have the same value for that function. So a continuous function might be the temperature at every location on the Earth. We are guaranteed, this is going to guarantee us that there must be 2 points on opposite sides of the Earth that have the exact same temperature. Humidity is a continuous function. We're guaranteed that there's 2 points on opposite sides of the Earth that have the exact same humidity. How much light a portion of the Earth is receiving is a continuous function. That means that we're guaranteed that there's always 2 points on opposite sides of the Earth receiving the same amount of light. Pick whatever weird continuous function you want across the surface of the Earth, and we're guaranteed that there's 2 points on opposite sides of the Earth that have the exact same value for that function. That's what we're going to prove. Feel like you have a grasp on what we're trying to prove?
Is this if these are continuous functions?
Right, so temperature can pretty accurately be modeled with a continuous function. If I take a thermometer, I measure the temperature here, and I move slightly, and I move slightly, and I move slightly, plotting all the values of temperature, it's going to change continuously. I'm not going to get 60 degrees here, and then move slightly and get 120 degrees. The change in temperature from point to point is going to be continuous.
It seems like there's a way to force it, but I'll keep listening.
It'd be really hard to force it. You might say, I want to make this spot really hot. And if you make this spot really hot, temperature, it's going to die down fast, but it's going to die down fast in a continuous way. It's not like the temperature here at this point is going to be 100 degrees, and then move 1 point to the right, and now we got 90 degrees. So it's going to change continuously.
Well, can you do this on a lot smaller scale, like a little ball?
Yes, this would also work for a little ball.
Okay.
You got some little ball, any continuous function defined across the surface of that ball, then yes, this is going to hold. There's going to be 2 points on opposite sides of the ball that have the same whatever it is.
It seems like there's a way you could force it so that it wouldn't be the case.
Let's prove that you can't force it so it wouldn't be the case. And we'll be shocked at how simple this proof actually is. So let f be a function from the surface of a sphere. Remember, S2 is the surface of a sphere. It's not S cross S.
Right.
S cross S is a torus. S2 is the surface of a sphere. So let f be a function from the surface of a sphere to R. Let f from the surface of a sphere to R be continuous. Understood that this has a standard topology on R, and this has a standard topology it would inherit from R3. Think about the sphere as a subset of R3. Okay. Then, there must exist some point on the sphere such that the value at that point on the sphere is equal to the negative of that point.
Right.
The value of the negative of that point. What's the negative of the point? It's a point on the opposite side of the sphere. Let me just really quick give you intuition for that. If I try to, this might be a hard picture, trying to draw XYZ there, and imagine some sphere trying to draw it in XYZ, it's going to be terrible. Wherever it goes through up here, let's say it goes through the point 0, 0, 1, so it goes 1 in the Z direction up there. Then going down here, the point on the opposite side of the sphere would be at the point 0, 0, minus 1. And so it's just take the negative of those coordinates, gives you the opposite point. That's what we mean. Terrible picture, but hopefully you've got the idea. And so if C is 1 point, negative C is a point on the opposite side of the sphere. Okay, so we are going to prove that there must exist some point on the sphere such that the value at that point and the value on the point exactly opposite on the sphere give the exact same value for whatever your continuous function is, doesn't matter what it is. All right, we're going to start by defining a g. It's a similar idea as to what we had up here. I'm going to define a g so it gives me 0 in a special case, and then I'm going to use this lemma, or this corollary, to finish off my proof. So I define g from S2 to R by g of x is equal to f of x minus f of negative x. Intuitively, what does g give me? It gives me the difference in the value of the function from 1 point and the point on the opposite side of the globe. Let's imagine that this was temperature. So I measure the temperature right here. So this point is x. I plug that in and it spits out 72 degrees. Let's say that I plug in the point on the opposite side of the earth, and over there it's cold right now. It's 27 degrees. Temperature here is, we'll say 77, temperature there is 27. What's the difference in our temperature? 50. So this is spitting out the difference in the temperature. It's taking the temperature where you are, the temperature where they are, or the temperature at the opposite point on the earth, and calculating the difference.
Okay.
Now notice that if I say the difference in temperature from me to someone on the opposite side of the earth is 50 degrees, what do they say the difference is? If they do their temperature minus my temperature, what do they get? Negative 50. So we always spit out negative of each other.
Oh.
If I spit out 50, they spit out negative 50.
Mm-hmm.
So that's going to be what my next line here says. So define g, so it's calculating this difference. And notice then that negative g, the negative of what they spit out, is going to be the same thing as what I spit out. They always spit out the negative of me. So the temperature where I am, the difference in temperature I measure, is going to equal the negative of the temperature they measure.
Yes.
In other words, we're going to measure a difference in temperature the same way. I say the difference between our temperature is 50 degrees. They say, no, it's negative 50 degrees. They're always going to spit out the negative of what I spit out. So g of x is set up, it's defined, so that g of x is equal to negative g of negative x. What I say the difference of temperature is the negative of what they say the difference in temperature is, if they're on the opposite point from me. Now we're just going to show that through the arithmetic, but that's the idea. So here's the arithmetic. We're doing negative g of negative x. So we're doing negative, and now this right here needs to be g of negative x. I'm taking this function, and I'm plugging in negative x for it. So I replace x with negative x minus f of negative negative x. Negative x is just positive x. Okay? So here's plugging in. Here's negative g of negative x. Now I'm just going to distribute the negative through. So distribute the negative through. This becomes negative f of negative x. And this becomes plus f of x. With me?
Yep.
Now I'm just going to swap the order here. So that's going to be f of x minus g of negative x. That's exactly how g is defined. The temperature that I measure minus the temperature that they measure. Okay, hopefully that all makes sense. So, if g of x is always equal to negative g of negative x, then that means that g of x and g of negative x have opposite signs, or they're zero. Because if I say the difference is positive, the person on the opposite side of the earth, they say, no, it's negative. Okay, so g of x and g of negative x have opposite signs, or they spit out zero. Notice that if they spit out zero, g of x spitting out zero is exactly what we're after. So either way, there has to exist some c in S2 such that g of c is equal to zero. Because g of x and g of negative x either have opposite signs or they're both zero. In either case, if they have opposite signs, there has to exist some point c between them where the value is zero. If they don't have opposite signs, that means they're both zero. And in either case, there's a point whose value is 0. My function g spits out 0 somewhere.
Yes.
I'm guaranteed that. So then there must exist some c on my sphere such that g of c is equal to 0. But what is g of c equal to 0 mean? Plug g of c in. What is g of c? It's f of c minus f of negative c. It's f of c minus f of negative c. Now, add f of negative c to both sides, and you get f of c is equal to f of negative c. And there it is. So, really simple proof for some pretty crazy results. Some results that seems like it would be extremely difficult to try and prove that. We got on that proof? Alright. We're now ready to then shift gears to the next concept. So we've been talking about connectedness, took a nice little break, talking about intermediate value theorem. Now we're going to talk about a stronger notion of connectedness called path connectedness. If a topological space is path connected, it's for sure connected. But just because it's connected does not mean it's path connected. Path connected is a stronger notion of connectedness. Okay, what's its definition? Well, first off, let's remind ourselves of what path is. This is an older definition. Let's remind us of it again. We've come across this, but good to refresh. A function f, whose domain is 0 to 1 to x, is a path in x, provided that f is continuous. So here's our interval 0 to 1. If f maps it into x in some continuous way, then we call this function a path. And pictorially, that's kind of what it would look like. F of 0 goes there, f of 1 goes there, and then we got all the points in between. It gives us a path in x. Okay, so that's the definition of a path. Now, definition of path connectedness. X, being a topological space, is path connected provided that for any 2 points in x you choose, there exists a path from one point to the other point in x. Pick any 2 points P and Q you want. There must exist a path from P to Q in order for x to be path connected. So saying that in high level language, when is x path connected? When you can connect any 2 points with a path. Pick any 2 points you want, there's some path connecting them. Okay. The set A as a subset of x is called path connected in x, provided that the subspace topology on A is path connected. Almost what you would have guessed. So if I'm looking at R2 and I'm wondering, is this set A connected in R2? I just look at the topology it inherits from R2 and then see if that topology is connected. So you would have almost guessed that that's the definition. Okay, now we're going to first show that path connectedness is a stronger notion of connectedness than just connectedness. Sorry, funny sentence. We're going to prove that if x, being a topological space, is path connected, then it is for sure connected. Alright, so let x be path connected, and assume by way of contradiction, it is disconnected. So it's just path connected, it's not also connected. Impossible.
Okay.
Setting up a bad picture. So let x be path connected, and assume by way of contradiction, it is not also connected, or in other words, it's disconnected. Okay. Remember, connected and disconnected, that's a binary. Have to be one or the other. Okay. Then, since it's path connected, pick any 2 points in x I want. So then, there exists a, b, and x, such that a and b are not, oh, sorry. This is because it's disconnected. So I know that my topological space is disconnected. If it's disconnected, what does that mean? It means I can separate it into 2 different components.
Yes.
Right? At least 2, maybe 10, maybe 100, maybe a million, but I can separate it into at least 2 different components that are non-empty. So if x is disconnected, then there must exist 2 points a, b, and x, such that a and b are not in the same component. Must be in different components.
Yes. Right.
Must not be in the same connected set.
Yes.
Okay. Then, since x is path connected, then there must exist some function p for path, there must exist some function p from 0 to 1 to x, where p is continuous, p of 0 equals a and p of 1 equals b. Or in other words, there must exist some path from a to b. This is what we mean by path from a to b.
Right.
Since x is path connected, a and b are in x, there must be some path connecting these two. Some path that starts at a and ends at b. Now, since this closed interval is connected, we already proved that, so is the image of the closed interval. When I run it through a path, its image still has to be connected, because continuous functions preserve connectedness.
Right.
And by definition, a path has to be continuous. So since 0 to 1 is connected, when we run it through our function, our path here, the image has to be connected. Which gives me that a and b are in the same component, because they're in the image of the path. And so they're in the same connected set.
Which is not.
Which is a contradiction.
Right.
We assumed that they were disconnected, and we assumed that the set was disconnected, and we chose a and b such that they're in different components. That there is no connected set connecting the two. Because if there is a connected set connecting the two, then they're in the same component. That's by definition of a component. So we assume by way of contradiction that x was disconnected, a and b were 2 points in separate components, and yet since there's a path connecting them, a and b must be in the same component. Contradiction. Therefore, x is connected. Okay, so if it's path connected, it has to be connected. What about the converse? If it's connected, does it have to be path connected?
Yes.
It seems like yes, right?
Yes. So
It seems like if I can't split my set up into two open sets, I should always be able to create a path from one set into the next.
What if you don't have a? What if you have a finite set where you can't? How do you create a path when you don't have a infinite plane area?
Remember, a path is just a continuous function with this. You can have a path from a point to itself.
Right.
So my function, here's a perfectly valid path in the real numbers. I do f from 0 to 1 to r by f of x equals 7. What does that path look like in R? Looks like that. Starts and ends there and stays there the whole time. Perfectly valid path. Stupid path, but perfectly valid. Satisfies all our rules. Okay. So, it turns out it is possible to have a connected topological space that is not path connected.
Can you go reverse through the path you've already taken?
What do you mean?
So I'm going to show you that I can have a connected topological space, but it's not path connected. I can find 2 points that cannot be connected by a path.
What I'm saying, so, and just by looking at that picture, I can see that if you run down trying to find a path there, you wouldn't be able to find a path somewhere else.
So let me explain what this is. So this is called the Topologist whirlpool. Now what we do is you give me an angle. It's in radians, but same concept works in degrees. I drew it for radians. You give me some angle, and I plot a point. So let's say you give me the angle 0.01 radians. So I go to an angle of 0.1 radians, and I plot the point 0.1 away from the from the origin. So notice what this spits out when I plug in a really small theta. Then we're plotting the point in polar coordinates. Well, when we get to 1, then we're going to plot 1 over 1 plus 1, comma, 1. When we do 2, we're going to get 2 over 2 plus 1, comma, 2. When we do 3, we're going to get 3 over 3 plus 1, comma, 3, right? 1 radian is roughly 58 degrees-ish. So at 58 degrees, when we plug in 1, at a radian of 1 or at 58 degrees, we need to go 1 over 1 plus 2 away from the origin, which is roughly 1/2. So at 58 degrees, plot 1/2. 1 is going out to here. This is a radius of 1. Sorry, put a little 1 right there for scale. So this is 1, go 1/2 in that direction. When our angle gets smaller, we go further away. As our angle gets bigger, we go further and further away. Notice that plug in a really big angle here. If I plug in 1 million, what do I get?
1 million over 1 million is 1.
Yeah, I get 1 million over 1,000,001 as my radius, and that's at whatever angle, 1,000,000, blah, blah, blah. We don't care about the angle, 0, 0, 0. The point is, as this spiral goes out, the radius, the spiral gets closer and closer to a circle with radius 1, but never quite reaches it. Gets closer and closer, never quite reaching it. You with me?
Yep.
So, A by itself is path connected.
Okay.
A is the spiral portion. When I union that together with S1,
That's a circle.
the circle, they're no longer path connected. There is no path you can construct from here, from a point in here to a point in here.
Get it?
A is the spiraling portion. And it spirals getting closer and closer to the circle, never actually reaching it.
Oh. And you can't, and they're not disconnected.
So if you were a one-dimensional being, and I stuck you on A here, and I said walk to the circle, take some path to the circle, there is no path you can get there. You'd be walking forever. After an infinite distance, you still haven't reached the circle.
Then I don't see how the circle is connected to A.
Okay, but first, you see how it's not path connected.
Okay.
One piece of intuition at a time. So you're good with the fact that if you're on the whirlpool here, the whirling part, it's impossible for you to walk to the circle. There's no path you can take. Okay. Now, let's try and say that they're not connected though. If they're not connected, what does that mean?
There's a separation on them.
I can separate them. I can split them into two open sets. Here's the problem that you have. A by itself is completely connected. The whirlpool part is completely connected.
Yes.
And S by itself is completely connected.
Yes.
So the only way that you could split them up is one component would have to have all of A and one component would have to have all of S.
Right.
With no overlap.
Yes.
Here's the problem you get. Pick any open set you want containing any portion of S. Doesn't matter how small you make it, you're going to capture some of A.
Right.
So you can't split it into A and S into two separate open sets.
Right. Right. Makes sense.
So they're connected. They're connected, topologically speaking. They're not path connected. Which our intuition, I think, likes path connected more. That's more intuitive of what we mean by connected. You can somehow get from one to the next.
Yeah.
Nope, you can't get from one to the next, but you also can't separate this into two sets.
It's cool.
It always seems like you can find. That doesn't connect to me.
Yeah, we're not going to prove this. You can read the author's proof of it. It's a lot of talk for a little bit of payoff. I think just seeing the picture and trying to get the intuition helps more.
Well, I don't care how damn close the swirl is to the circle.
It never reaches it.
It never reaches it, therefore it's not connected.
No, because you can't.
Right, you're trying to use the notion of path connected as your definition. But remember, what exactly does it mean for it to be disconnected? It means you can split it into two open sets.
Well, okay. No matter how close you are to the circle, you could always find another.
So if you were to split this into two separate components, all of A has to show up in one component and all of S1 has to show up in another component. They can't show up in the same component.
Right.
Yeah, that makes sense. They wouldn't be in the same component, therefore they're not connected.
Right, so we're trying to say that A and S can be their own separate components. That would mean it's disconnected, if we could say that.
That's right.
What does it mean for A and S to be disconnected? It means that we can find open sets containing them that have no overlap. Our problem is any open set you choose that contains any portion of S, doesn't matter how stupid small you try and make it, it's also going to contain some of A. I cannot split S off from A in any way.
I hate this.
So these are your weird examples. It's very strange examples where you get a topology that is connected but not path connected. They're weird fringe examples.
I literally essentially can't find a path from A to S, but they're connected.
Correct.
Almost makes me wonder if there's something wrong with the definition.
So, there's a reason that it took topologists so long to come up with these definitions. There's a reason it took so long for topology to develop as a field. You're constantly fighting your intuition.
Which is nice, because our intuition sucks.
Sometimes it's real nice.
It's a shortcut.
Right. Okay. Let's look at another one, similar concept. So this one is called the topologist sine curve. Here's exactly what it is. X, we're applying all the points x and sine of 1 over x for all values of x greater than 0.
Yep.
So that gives us a sine curve. Notice as x gets really small, 1 over x gets really big.
Yes.
So as our x gets closer and closer to 0, our sine of x starts going back and forth faster and faster and faster. And so we just get our frequency is increasing faster and faster and faster as we get close to this. The closer and closer to this, our frequency approaches infinity.
Yes.
So that's A. I is just the closed interval from -1 to 1. Right there.
Mm-hmm.
Same argument. It is impossible to take a path from A to I. And yet, A union I is connected. So it's not path connected. There's no path from here to here. And yet it is connected. Same argument. Doesn't matter how stupid small of an open set you try to create around the interval I, you'll always get some of A.
Mm-hmm.
It gets arbitrarily close to I, never quite reaching it.
So, if you were to create functions that were essentially disconnected, but have some type of infinite path towards connectedness, then they eventually become connected, even though there might not be a path.
Correct. You set up these cases where your function gets so you need two sets. Set A and then some other set, and I'll call it set B. Set A and B. What do you need to set up? You need A to be getting arbitrarily close to B at every point on B without ever actually getting there.
Yes.
That's roughly what has to happen.
Right.
Okay, so there's some feel-good examples of connectedness versus path connectedness.
It almost makes me wonder if
That didn't shake.
you were to go all the way 2, 3, but not 2, 3, but then have another component that's 3 to something, that they would also be connected, because there's nowhere that you could find between 3 and the other
Yeah.
range. You couldn't find any. You couldn't find a space.
Yeah.
As long as it's getting arbitrarily close everywhere, then you're in trouble. And it probably doesn't have to get arbitrarily close everywhere. That probably just makes it a lot easier to prove.
Well, so I'm thinking on a number line. You know how we always say, how do we phrase it?
Open interval or what?
It's an open interval, so it's like from 2, and then up to 3, let's say, but not 3.
Okay.
Are we including 2?
Say yeah, include 2, doesn't matter. But then we're saying up to 3, but not 3. So yeah, and then we create another one that is 3, and then say up to 4.
Including 3 or not including 3?
Including 3, but he did it right. I would argue those are connected.
They are. Right? They have to be. Because you can't find a separation, because 3 is a separation. They've got to be connected.
You've got to say that those are connected.
Yeah.
Now I want to think about it.
Well, there's no separation on it.
So here's my thought. I want to say U1 is equal to the union I'm not sure how to say this, the union from n equals 1 to infinity. So we're taking an arbitrary union of infinitely many sets of the interval 1 over n plus 3 to, now this one doesn't matter, 6. And then u2 would be just 0 to 3. So when you plug in 1 for n, you get 1 over 1 plus 3 is 4.
Right.
So that is giving you 4 to 6, this open interval.
Yeah.
But union that with, now instead of adding 1 to 3, we only add a half. Then we only add a fourth. Then we only add an eighth. Then we only add a 16th. Then we only add a 32nd.
Uh-huh.
Dot, dot, dot. This is an open set
Yeah.
because it's an arbitrary union of open sets.
Uh-huh.
This is an open set.
And it never includes 3. U1, right? U1 doesn't include 3.
Correct. It'll never equal 3.
In the limit, it gets 3.
Yeah, but it won't, well,
This will end up equaling. Will it? No.
It'll approach 3, yeah. The limit is, well, is it? Yeah, the limit's 3.
Now what do you think about this? I keep thinking one way and then I think, no, that's wrong. And I think, wait, that's right. Then I think, no, that's wrong.
Yeah. That doesn't, there's no way U1 includes 3. Or,
Yeah, I can't include 3.
right, well, yeah, right.
Right.
So,
And so 3 is a point in here.
So 3
It will
would
never
be-
be captured in there.
Right, so 3 would be separation then.
So that would be a connected set.
that's connected.
Wait, what? U1 and U2 would be disconnected.
Oh, duh. We're way overthinking this. This set, A union together with B, is connected. A duh. Because it's just the interval from 2 to 4.
Yeah,
All
yeah, right.
right, brain fart.
So
Yeah.
it's connected.
Obviously,
Yeah.
the union of those two is connected, yes.
Yeah.
Because it's all the numbers from 2 to 4.
But there is no path. Connected path.
There is a path when you take the union of these two.
Wait. Well then how are these ones not have a path then?
Right. So, very different thing going on here versus there. Sorry. Can't believe I just...
That's fine. We'll bring
Ah, okay.
I do it all the time.
Over here, there is no path from A to S1.
How about when you union?
When you union them, that's what I'm saying. So we're looking at A union S1. You start out here, unioning them together, and there's no path you can take that gets you over here. Because you gotta get through this infinite spiral first before you get to S. Which you can't do.
Right.
Same problem here. You have to get through this infinite oscillation first before you get to the interval.
Right.
Here we don't have that problem. Obviously you union them together, they're connected, but
But then we don't have to go through this infinite path. What's wrong with going through an infinite path? Why is that all of a sudden bad?
Because you will never.
that's what's ultimately breaking it. That's intuition for what's breaking it.
What makes it the fact that it's an infinitely long path that all of a sudden that's no longer possible, considering we created something that's infinite.
So if we think about one infinite path as the real numbers, the whole real number line is an infinitely long path. So if I tried to make the real numbers an infinitely long path, I have to come up with a continuous function from 0, 1, the closed interval, to R that's continuous. And no such continuous function exists.
Because you have to map 1 to infinity.
Yeah, you end up being forced to map 0 to negative infinity and 1 to infinity, which doesn't work. Or you'll run into some problem where you have to do something like that.
Right. So that you can't.
And so this, one of the things we talked about is 0 to 1 is not homeomorphic to R. Those are very different things. But the open interval 0 to 1 is homeomorphic to R.
Right.
So you can make a continuous function from this to this, not from this to this.
Right.
Now, of course, not every infinite path is all of R, but that's just intuition to help you see the thinking.
So you can't have an infinite path.
I don't want to say that, because What's meant by infinity? I cannot have a path to the real numbers, to all of R.
Can you have a path that's infinitely long? That never ends?
Remember that length is a concept that only exists in a metric space.
I know.
So, I don't know. What I do know is that you cannot have a path from the closed interval 0, 1 to R.
Right.
That I know.
Right.
I don't see how that proves the point.
Well, if you're going along
Well,
this
if you think about, what do we mean by an infinite path? If you think about that's the same as going over all the real numbers. That's an infinite path. Going over the whole real number line.
True, that's true.
So if you think about that as your infinite path,
Okay, I see now what you're saying.
then we know that there is no continuous function from the closed interval 0, 1 to R. Every path is of the form, a continuous function from 0, 1 to whatever. So you can't have a path to all of R. No such path exists.
But you can have a path
To any 2 points in R, pick 2 points in R and I can connect them with a path. But I can't connect all of R with a path.
Right. And you're saying the 0 and 1 is a representation of the path?
No, a path, by definition, is a continuous function whose domain is 0 to 1. So it has to be continuous, and its domain has to be from 0 to 1, that closed interval.
Interesting. Okay,
So the intuition for what's breaking this is you're forcing it to traverse an infinite path before it gets to the next set.
yes.
And so just intuition, but yeah, we can say there's no infinite paths.
Okay, and the only reason that way we would know that for sure is we're saying that this closed set of 1 to 0 to 1 is for, in fact,
There's close at 0 to 1.
why exactly cannot that not be in,
There is no continuous function from the closed interval 0, 1 to R.
okay, do you mind explaining that?
I can't right now.
Okay.
When we first went over continuous functions and talked about how these two are homeomorphic to each other, we tried to touch on that concept to give you the intuition for it.
Yeah.
But again, this whole concept was just trying to give you intuition for that concept. That's the important one. And why this one doesn't work comes down to the fact that any open set that contains some of this has to contain some of that.
Yes.
So this would have to be a component, this would have to be a component, but you can't separate them. So they're not components. That's the important part from that.
Alright. Okay,
Okay.
I'll let that.
Very unintuitive stuff. Alright, continuing with path connectedness. Next one. If f from x to y is continuous and x is path connected, then the image of x is path connected in y. Or in other words, continuous functions preserve connectedness. Or sorry, we already proved that. They preserve path connectedness. Now that's what we're proving.
Right.
Okay, so let x be path connected, let f be continuous, and let p and q be any 2 points in the image of x.
Sure.
I'm trying to prove that there is a path connecting p and q.
Oh, it's easy.
That's what we're after. Remember, I know x is path connected. I'm trying to show f of big X is path connected. How do I show a topological space is path connected? I show, pick any 2 points you want, I can find a path connecting them. Therefore, it's path connected. That's how we prove it. Okay, so let p and q be any 2 points in f of x. My job is to find a path that connects p to q. And we're just going to call the pre-image of p A, and we're going to call the pre-image of q b.
Okay.
They have to have pre-images because they show up in the image of the function.
Right.
So p had to be mapped to from something called A. Q had to have been mapped to from something, call it B. Alright, now we're defining a G here. Since I know that X is path connected, I know that A and B have to be connected by some path.
Yep.
Remember, we're trying to show P and Q are connected by path. Maybe draw a quick sketch of what's going on over here to keep track of which points are where and what we're talking about. So we've got two topological spaces that we're talking about. We're talking about X over here, and we're talking about Y over here. I know x is path connected. Let's say f of x, so f is some function here, and we'll say f of x is this portion of y. Here's f of x. Maybe all of y, maybe not all of y. F of big X. When we run this whole space through our function. With me?
I thought F had to be onto.
No, f is just continuous. The preimage of open sets are open. If it was one to, well, yeah, onto is a different property.
It has to be 1 to 1.
No,
Or, sorry.
it doesn't have to be one to one, and it doesn't have to be onto.
Does it have to be bijection?
No.
No. Sorry.
If it had to be a bijection, then all these times we would be able to say if x was connected, then y is connected. If x was Hausdorff, y was Hausdorff. We've always used this type of terminology, saying if the domain has this topological property, then the image of the domain has a topological property.
Sorry.
Homeomorphisms give it to you both ways, because with the homeomorphism you have the continuity and the bijection.
Sorry. Yeah, right.
Yeah, no worries. It's always good to keep that clear in your head exactly what we're talking about. So f is just continuous. That's all we know about it. And it's mapping x to f of x over here. Maybe all of y, maybe some portion of y. Now, what am I doing? I'm picking any 2 points over here I want. P and Q. Let's get ready to talk about G. All right, P and Q. Now, since P is in the image of f of x, then there had to be some point over here, A, such that A is equal to the preimage of P. And there also had to be some other point over here, B, where B is equal to the preimage of Q. So we have A and B over in X. We know X is path connected. We're trying to show f of x is path connected.
Right.
Since X is path connected, I know that there exists some path connecting A to B.
Yes.
I may call that path G. Okay? And then I'm going to basically run G through my function f. And it turns out that that is going to spit out a path over here.
Of course.
Call it f after G, or f composed G. So f composed G is going to be the path over there. That's the way this is going. So, back to where we were. So A is the preimage of P, B is the preimage of Q. Now, since A and B are in X, and X is path connected, then there must exist some function G from 0, 1 to X where G is a path from A to B. Let H be F composed with G. So H is going to be our path over there. Let H be F composed with G. And notice that H's domain is the same as the first function we run's domain. In this case, G. So the domain of H is the same as the domain of G. The domain of G is 0 to 1, so the domain of H is 0 to 1.
Yep.
And the image of H, its codomain, is going to be the same as the second function we run, which is F. And F's codomain is Y. So H is a function from 0 to 1 to Y.
What's the codomain?
Sorry, what?
What's a codomain?
The codomain, the other set. This is the domain, this is the codomain. Your image or your range is always a subset of your codomain. So, simple example of one you work with all the time. If I tell you f of x is equal to x squared, its domain is all real numbers. You can plug every real number into that. Its range is just all the real numbers greater than or equal to 0. But we can still call its codomain all real numbers. This is a function from the real numbers to the real numbers. It just doesn't map all of them.
Oh.
So codomain, it's the set that you're running to.
Okay. Gotcha.
Doesn't necessarily have to be. If your image is your entire codomain, then you're onto. That's one way to define onto. The image is the entire codomain. Okay. Good. So we've got H is a function from 0, 1 to Y. We know H is continuous. How do we know that? We already proved that the composition of continuous functions is continuous.
Right.
So since H is the composition of f and g, both of which are continuous, H is continuous. So H is continuous since f and g are. Also notice, what is H of 0? h of 0, let's see, by definition, h is f after g. So h is f of g of 0. What is g of 0? What is g of 0? It's wherever the path g starts.
A, right?
It's a. So g of 0 is a.
Yeah.
And what's f of a?
P.
P. F of a is a preimage of p, so f of a is p. Similarly, what is h of 1? It's f of g of 1. What's g of 1? It's b. And what's f of b? It's q. So h is a function from 0 to 1. H is a continuous function whose domain is 0 to 1, whose codomain is y. It starts at p and it ends at q. That's exactly what we mean by a path from p to q.
Yes.
So therefore, h is a path from p to q in f of x. Therefore, f of big X is path connected in y. Any 2 points could be connected by a path. Any questions on that one? All right. Now, the same way that we created the equivalence relation, we used tilde sub c for x is in a same connected set as y.
Right.
We're going to use this tilde sub p to mean x is connected by a path to y.
Okay.
Okay, so we define tilde sub p, this relation. This is connected by a path relation, to be a relation on x where x is related, little x is related to little y if and only if there exists a path in x from little x to little y. What does it mean to say they're related? You can connect them with some path. That's all it means.
Okay.
So, no, we're really quick going to explain how this is an equivalence relation. We remember what an equivalence relation is. 3 properties. What does an equivalence relation have to have?
It has to be reflective.
Reflexive.
Transitive.
So every point has to be related to itself.
Yes. Transitive.
Transitive, that's the 3rd one. Which means that if A is connected by a path to B and B is connected by a path to C, A has to be connected by a path to C.
And symmetric.
And then symmetric. Which means that if A is connected by a path to B, then B has to be connected by a path to A.
Yes.
So we need to show that those 3 properties hold for this relation, therefore it's an equivalence relation. Once you show it's an equivalence relation, you can talk about its equivalence classes. Remember, when we talked about the components of a topological space before, they were the equivalence classes of the is contained by a connected set relation from before.
Right.
Now we're going to come up with different equivalence classes, which are going to be the path components of the set, and that is going to be they are connected by some path. The equivalence classes for that. So going back to these 2 examples over here, while this has no components, A and S1 are going to be path components. Okay, so let's take this one step at a time. Let's first show that is connected by a path relation is reflexive. So let A be any point in X. I'm trying to show that there exists a path from A to A. Therefore, A is related to itself. So let A be any point in X. Then the path from 0, 1 to X by P of X equals A is a path. Your constant function is a continuous function.
Right.
F of X equals whatever, 3 is a continuous function. We've already shown that constant functions are continuous. So that's continuous. It just maps everything to A. 0 goes to A, 1 goes to A. So it's a path that starts at A, ends at A, and stays at A everywhere else in between.
Yes.
So it's a path. Therefore, for all A in X, A is connected to A by a path.
Yes.
Namely, this path.
Yep.
Okay, so that one's pretty simple. Let's do the next one. I need to show that if A is connected to B by a path, then B is connected to A by a path.
Yep.
So let A be path connected to B. What does that mean? That it means that there exists some path 0, 1 to X such that it starts at A and it ends at B.
Yep.
My job is to find a path that starts at B and ends at A. So now I'm going to create some new path, F, from 0, 1 to X by F of X equals 1 minus X. Or sorry, F of X equals P of 1 minus X.
Okay.
So then F is going to be a path from B to A.
Makes sense.
Let's make sure we see that all the way. So F of X is equal to P of 1 minus X. So let's see, what is F of 1 equal? F of 1 is equal to P of what? 1 minus 1.
Which is 0.
1 minus 1, which is equal to P of 0, which is equal to, what's P of 0? A. So F ends at A. Let's look at F of 0.
Oh, I see.
F of 0 is equal to P of 1 minus 0 is equal to P of 1 is equal to B.
Yep.
So it starts at B and it ends at A. It's just running over the path backwards.
Yep.
And then how might we argue that this is a continuous function? Well, you can think about this as a function 1 minus x embedded in P. So I know P is continuous. This is 1 minus x composed with P. Composition of continuous functions is continuous.
Yep.
Okay, last one. Let A be path connected to B and let B be path connected to C. What does that mean? Well, what are we trying to show? I'm trying to show that A is path connected to C. So let A be path connected to B and B be path connected to C. Well, since A is path connected to B, there must exist some function f from 0, 1 to x, and there must exist some function z from 0, 1 to x, such that f is a path from A to B, and g is a path from B to C.
Yep.
So we have A, B, and C are points in here. I know that A to B, there's a path from A to B. I know there's a path from B to C. I'm trying to show that there's a path from A to C. And naturally, the path is going to be do the whole thing. Okay. So we're going to define some new function h here. What is h going to do? H from 0, 1 to x by h of x equals this thing. What this thing is going to do, remember this portion over here we called f, this portion over here we called g. H here is going to glue these two together at the point B into one path. That's essentially what it's doing. So rather than, well, walk you through it one step at a time. So h of x, what do we do? If your x is between 0 and 1/2, so we're going to take the first half of the interval from 0 to 1, and we're going to map it to this portion. And then we're going to take the second half of this interval 0 to 1, and we're going to map it to this portion. And then the whole thing's going to map to the whole thing. That's the way that this is going to work. So define h from 0, 1 to x by h of x is equal to f of 2x when your x's are between 0 and 1/2, and then g of 2x minus 1 when your x's are greater than or equal to 1/2 but less than or equal to 1. So this maps the whole domain because our whole domain is just 0 to 1. Now let's see how this works. First off, let's see what h of 0 is. So h of 0, let's see, 0 is between 0 and 1/2, so we use the top function. H of 0 is equal to f of 0 is equal to a. So far we're good. Let's plug in h of 1/2. H of 1/2, notice that that works up here. So plug in 1/2 for x, what do we get?
1.
F of 1. So h of 1/2 is the same thing as f of 1, and what is f of 1?
B.
B. But notice we could have also thought about h of 1/2 down here. H of 1/2 is also a number greater than or equal to 1/2 and less than or equal to 1. So we could have also plugged into this function. 2 times 1/2 is 1 minus 1 is 0. So h of 1/2 is the same thing as g of 0, which is b. And then finally, what do we get for h of 1? When we plug in 1 for x here, that means we use this function. 2 times 1 is 2, minus 1 is 1. It spits out g of 1. What's g of 1? It's c. So h here maps 0 to a, 1/2 to b, and 1 to c. It maps all the points in between to all the points in between.
Right.
Okay, so there we go. So since f and g are continuous, so is h. That's by the pasting lemma. You paste two continuous functions together. If f was continuous and g was continuous, and where they overlap, they spit out the same value, then when you glue them together like this, it's still continuous. That was a pasting lemma. So then h is a path from a to c, and so we have a is related to c. So if a is related to b and b is related to c, then a is related to c. Transitivity. So there we go. It's an equivalence relation, which means it has equivalence classes. And so the equivalence classes of this relation we call the path component of x. So we have a notion of the components of x, and now we have a notion of the path components of x. Those two spaces over there, we couldn't split it into two components, but we could split it into two path components. Okay. Good with that? Okay, now we start the next chapter, the last chapter we'll be covering, and our last big topological concept, the last of the big 3 C's. The 3 C's of a beginner topology course are continuity, connectedness, and compactness. So introducing the last one, compactness, the last chapters on compactness, and after that we'll be done. Compactness is also the least intuitive of all the definitions we talked about. When I tell you the intuition for how we think about it, and then when I show you the definition, you're going to think those have nothing to do with each other. It's absurd. And in terms of the definitions we talked about, compactness is the newest one. As far as math goes, this is a kind of new definition. It's about 100 years old.
Wow, that's a spring chicken.
Yeah, spring chicken here. Compactness. Very strange definition. The intuition for it, not too bad when we're talking about the nice topological spaces we know and love. But when I give you the definition, I'm telling you, it's right out of left field. Okay, intuition. In R2, this set right here is going to be compact. This is a closed rectangle containing all the points inside of it.
Okay.
This circle by itself is going to be compact. If I just pick some random points out of R2, put them together in a set, those points are going to be compact.
They are?
Yes. One more time. Here's what this is doing. Take some square, some rectangle whose base has a length of 1. So it goes from 0 to 1. So we've got those lines, not any of the points in between here. Put a line at 1/2, include all those points, and at 1/4, and at 1/8, 1/16, 1/32, 1/64, 1/128, and add all infinitely many lines. That is still a compact set.
Okay.
What sets are not compact? An open ball is not compact.
Okay.
This shape, missing those boundary points, is not compact.
Okay.
This shape, missing these boundary points, going on forever that way, is not compact. If I took this one and I force it to include its boundary points, but it still goes on forever, it is still not compact.
Okay.
Okay, intuition. In R2, in standard topologies, compact sets are going to be closed sets that are also bounded, that aren't infinitely large.
Okay.
So all these are closed sets that don't go off towards infinity. This one is open, it's not closed. This one's not closed. This one is closed if we include those boundary points, but it goes off to infinity, so it's not bounded. So if we were doing a calculus course and I was defining compactness, I'd say compactness are closed bounded sets.
Yep.
In the standard topology, that's a good definition. But we're not in the standard topology, we're in every topology. And so what's our definition of compactness? That gets down to this notion of, oh, it's closed and bounded when we're in the standard topologies. Here's the definition of compactness.
What's the point of this?
Yeah, like what does compactness even mean? Like, I think
In the standard topologies, it means closed and bounded.
But why is that useful?
Why is it useful?
Yeah.
Uh,
I mean, it's not like when I think of compact, I think of something that's pressed together.
Yeah, in some sense it's pressed together.
which we don't even have that in topology
Oh, yeah.
Why not?
because there's no such thing as space.
There's no such thing as space, but you can still have points in some sense packed together.
No,
Well, every
Literally
point
cannot.
infinitely is packed. I'd rather.
So we'll get more comfortable with this compactness notion as this chapter goes on.
Okay.
It has some very useful properties. A very famous one is what's called the extreme value theorem. So the same way that the intermediate value theorem over there came from a set being connected, the extreme value theorem, which is another famous and very valuable theorem from calculus, comes from compactness. And any sort of efficiency program, anytime you're looking for efficiencies, looking for a max or a min, a peak or a min, you're using the extreme value theorem.
Okay.
So it's used in tons of applications. You use the extreme value theorem left and right. This is getting down brass tacks what exactly the extreme value theorem is. And then compactness, it's also very useful in just analysis in general. Anyways, but its most famous use case is definitely the extreme value theorem. Okay, anyways, so before we give you the definition of compactness, we need to find a cover.
Okay.
So given some topological space, let A be a subset of X, and let O be a subset of the power set of X.
Okay.
So A is a subset of X, O is a collection of subsets of X.
Okay.
A might be one of the sets in O, might not. Okay. We say O is a cover of A if and only if A is a subset of the union of O. If I union up all the sets in O, and unioning up all the sets in O gives me back at least A, maybe more, but at least A, then A is a cover of O. All the sets in O, if I were to take them and lay them out, they would have covered all of A.
Oh yeah, okay, that makes sense.
Let's look at a picture over here really quick.
It's like a subset.
Here's A, and in O, I put the sets O1, which is this set, O2, which is this set, and O3, which is this set. Notice if I union O1, O2, and O3 together, it covers all of A.
So A is like a subset of O.
A is not a subset of O1, A is not a subset of O2, A is not a subset of O3. O is equal to O1, O2, O3, all those together. If I union all three of those together, then A is for sure a subset of that.
Okay.
Okay, so O is a cover of A, if and only if A is a subset of the union of all the sets in O. Union up all the sets in O, A is a subset of it. Then O covers A.
Yeah.
O is an open cover of A, if and only if O covers A, and O is a subset of the topology. In other words, everything in O is an open set.
Right.
What do you mean it's an open cover? It's a cover that only uses open sets. So if we're thinking about this in terms of R2, O was a cover, but O is also an open cover, since all my O's happen to be open sets.
Right.
So O is a subset of tau. Remember, tau is our set of all open sets. If O is a subset of tau, everything in O is an open set.
Right.
So O is an open cover if and only if A is a subset of the union of O, and O is a subset of tau. Okay. And then finally, if O covers A, and O prime is a subset of O, such that O prime also covers A, then O prime is a subcover of O.
Okay.
So looking at our picture again, notice O, using the set O1, O2, O3, is an open cover of A, but notice that O3 here isn't really adding anything. It's completely covered by O1 and O2. You don't really need O3 in there to cover it. So O prime equal to O1, O2 is a subcover. This is a subcover of this because it still covers all of A. If I instead would have said, let's look at O1, O3 and got rid of O2, this is no longer a subcover of this.
Right.
Because we don't still cover A.
Right.
Okay, so that's what's meant by a subcover. Now, the awful definition. The topological space X is said to be compact, provided that every open cover of X has a finite subcover. X is compact if every open cover has a finite subcover.
Can you have infinitely large covers?
Yeah, a cover could have infinite elements in it.
So, well, like,
Okay. Another way we can think about this is X is not compact if there exists any open cover that has no finite subcover. Let's do an example, and let's read the definition again, and I think you'll start to click. So let's do an example. We're going to show R with the standard topology is not compact. Okay? How do I do that? If I'm going to show something's not compact, I need to come up with an open cover that has no finite subcover. So the open cover I'm going to choose is all these intervals. So this is the open interval -2 to 0, together with -1 to 1, 0 to 2, 1 to 3, 2 to 4, 3 to 5, 4 to 6, 5 to 7. So they're open intervals of length 2, starting and ending at every integer. And I drew them out pictorially in blue here. Let's get rid of this other stuff. Just making a mess. So here's our real number line R, and I drew in blue all these sets. -2 to 0, that is this set right here. -1 to 1, that is this set right here. 0 to 2, that is this open interval right here. So each one of these little line segments represents one of the sets in here. You with me? Now notice that they cover all of R. Pick any point in R that shows up in one of these sets. 3 shows up in this set up here. 2 shows up in the bottom set right here. You with me? So you see how all these intervals, if I union them all up, it covers all of R.
Yes.
Now, notice what happens if I just get rid of one of those intervals. Just get rid of this one. Get rid of the interval 0 to 2. Now, none of these sets contains the point 1.
Right.
So this is an open cover. And if you get rid of even one set, it doesn't cover R anymore.
Right.
So this is an infinite cover.
Yes.
It has no finite subcover.
So therefore it's not compact.
You can't pick a finite number of sets out of here and have it still cover R.
Does it even have a subcover?
Technically, every cover is its own subcover. O is a subset of O.
Does it have a subcover that isn't?
Does it have a proper subcover? No, because we just showed intuitively that if you get rid of even one, then it's no longer a cover.
Right. Okay.
Now you might be thinking to yourself, why didn't I just say O is -infinity to 1 and -1 to infinity? Notice this covers all of R. And it's finite. So isn't R compact?
What about 1?
1's in here. This is -1 to infinity.
Oh, negative 1, sorry.
So 1's in here for sure. -1's in here for sure. So notice that this covers all of R. This is definitely a cover of R. And it's a finite cover. Let O be its, notice that O is its own finite subcover.
How?
This is finite.
That's not finite.
There's only 2 sets in it.
Oh.
Remember, O is a collection of sets.
Yes, sorry.
1 set, 2 set. How many elements are in O? Just 2. 2 infinite sets, but just 2.
Right.
So O has a finite number of things in it.
Okay.
So O is a finite subcover of itself. O covers R, and O is a finite subcover of itself. So doesn't this prove that R is compact? This is how you may be tempted to think. Read the definition carefully. X, up here. The topological space X is said to be compact provided that every open cover has a finite subcover.
Okay.
It doesn't mean you can find an open cover that has a finite subcover. It means every single possible one has a finite subcover.
Okay.
So here's one. Here's one that happened to have a finite subcover, but this one doesn't have a finite subcover.
Right.
It's only compact if every open cover you can possibly come up with has a finite subcover.
Yes.
If you can find even one case where that doesn't happen, then it is not compact. So what does it mean to say that X is not compact? X is not compact if there exists any open cover that has no finite subcover.
Yes.
So that's typically how we prove something is not compact. Usually easy to show it's not compact, then it is compact.
Right.
Because showing it's not compact, we just have to come up with one example. To show it is compact, I need to show that for any open cover you choose, I can always find a finite subcover.
Right.
That's hard. Okay. We're just going to focus on feel-good examples and then end it there. We're not going to do any proofs with this because I want to take you through the definition of compactness twice.
Yeah.
Because very unintuitive one. Very unintuitive how that is somehow giving you sets that look like this.
Well, kind of makes sense, I guess.
All right. Let's go over some more examples then. So, consider X tau, so some topological space, where X has the elements x1, x2, x3, xn. Or in other words, what I'm getting at is X, the size of X is equal to 1, is equal to n. So it's a finite set. X does not have infinitely many things in it. It has 100 or 1,000 or a million or a trillion, but definitely not infinite. It's finite. Okay, what do we think? Compact? Not compact? Need more information?
Remind me what the absolute symbol means.
Oh, the cardinality. It's saying how many things are in the set.
Yeah, you told me before, I just forgot.
Yeah, it's like, I don't know the language you use. When you have a set, you have like a dot length function or a dot size function.
Yeah.
Count.
Count.
Yeah.
That's given the count.
Like, yeah.
Okay.
So what do we think?
Like, it has to.
Compact or not compact?
So it has to just cover a set A, right? Or is
We
that-
want to say, is X compact?
Oh,
So X is the set we need to cover.
so we need to. Yeah. Well, no. Like,
Does every open cover of X have a finite subcover?
every open cover. I have no clue.
Well, we know X is finite.
Yeah.
So let's think about the power set of X.
Okay.
What's the power set of X? It's a set of all possible subsets.
And it's fine.
And it's finite. In fact, we know the exact size of the power set of X. This is equal to the size of X to the power of 2.
Really?
Yes. A simple way you can see that is, I'm counting how many subsets I can make. Let's do a more concrete example. How many subsets can I make of the set A, B, C? Let's think about that for a second. So I'm going to create some subset of this set. Right?
Yeah.
And I need to make 3 choices. My 3 choices are, should I include A, yes or no? So I have 2 choices on whether or not I include A. Should I include B, yes or no? That's 2 choices. Should I include C, yes or no? That's 2 choices. So for every element in here, I have 2 possible choices I can make. And depending on each of those choices, I can make each of the different subsets. And so there's a total of 8 possible subsets I can make from this set.
Okay. Gotcha.
So if X has a size of n, then the power set of X has a size of
And 2.
n squared.
Okay.
N to the 2.
Alright.
Okay, but you've got the right idea. The power set of X is some finite number. Our open covers have to be
Bottom one.
right here. Our open cover has to be a subset
All
of the power set.
Oh yeah.
Wait.
The only thing we can cover this with is subsets of X.
Right.
That's where I'm getting all my subsets from, is the power set. They're all subsets of X. There's a finite number of subsets of X I can choose.
So you're covering X with subsets of X?
Yeah, that's what we're always doing. Well, in this case, I was covering A with subsets of X. But if I was talking about is X itself compact, I'd be covering it with subsets of itself.
Okay. So I think that would be correct then.
So it is definitely compact. Since every open cover is finite, then every open cover has a finite subcover, namely itself.
Wait.
Because every set is a subset of itself.
What in
So subcover, subcover. A cover is also its own.
Every set is a subset of itself.
yes.
Okay. That's,
Subsets kind of like less than or equal.
okay. Okay. So just to go up there a bit, O is considered compact, correct?
O is not compact. O is how we argue something is compact. X is what we're saying is compact. In this picture up here, we were saying A is compact or not, because that's what we were covering.
Yes.
Okay.
But here, when we were talking about is R compact, we were covering R with subsets of itself.
Yes, right.
Here, we're talking about is X compact, we can only cover it with subsets of itself.
So why
As a finite number of subsets, so every open cover of X has a finite subcover.
Is there any open cover that isn't just the entire set X?
Sure, depending on your topology.
Oh, that's right.
But since all of X is always in the topology, then there's always at least one open cover.
X.
The set containing X.
If you have the trivial topology, is X the only cover?
No? I could have an open cover O equal to X together with the empty set. They still cover X.
So there's two open covers?
So there's only two open covers we can make. The set containing X and the set containing X in the empty set.
Just
Those would be the only open covers of X.
right.
But they're not the only covers of X. Open cover means we only use open sets. Covers of X means
Anything.
we can use any subset of X.
Any subset of X.
Yes.
Right. Okay. Yep.
But our definition is specific to open covers. The topological space X is said to be compact provided that every open cover has a finite subcover.
Yes.
So our definition of compactness, we're limiting ourselves to open sets.
Okay. Yep.
Okay, so we got that one. Let's try one more now. Let's look at the open interval 0 to 3 in the standard topology on R. So we're looking at just a small open interval 0 to 3 on the real number line. So we're picking from 0 over to 3, talking about those points. So just ask that. Is that compact?
So you have to find an open cover that has a finite subcover?
Does every open cover of that set 0 to 3 have the finite subcover?
And does the subcover have to cover the entire thing?
Yeah. If it doesn't cover the entire set, then it's not a cover.
Right.
So does every open cover have a finite subcover? What do we think?
I'm gonna, not including 0 or 3.
Right.
So that I'd say no.
And you're correct there. The answer is no.
Right.
So here's my open cover.
Right.
Yeah, I hate to say that, it's just my intuition. I don't
Yeah.
know for sure why.
That's good. That's what these examples are largely to do, is help you develop intuition. So O is equal to, let's write out what O is. First off, we're doing these intervals for every n in the positive integers.
Okay.
So plug in 1, and what interval does that give me?
1 over 1.
1 over 1, which is 1, 2. 3 minus 1 is 2, over 1 is just 2.
1 over 2.
Alright, so we got 1 over 2. And now our next one is
1/2.
1/2 over
5/2.
Let's do one more. 1/3 over
8/3.
Oh crap, did I do this one wrong? Oh, no, I don't think I did. Okay, let's just jump down the road and plug in 100. That's the open interval 1 over 100, right?
Yeah.
300 minus 1 is 299
over 100.
over 100.
Yep.
And you see that this left-hand element is getting closer and closer to
0.
0, and the right-hand element is getting closer and closer to
2?
3.
Or
3.
3, yeah, sorry.
3.
Right? That's the same thing as 2.99.
Yeah.
Yeah.
So if we do this for all infinitely many, that's an infinite cover, and it's going to cover the interval 0 to 3. Any number you pick between 0 and 3 will eventually be covered in one of these.
Okay.
And yet, you have to use infinitely many elements to get all of 0 to 3. If I were to try and just pick a finite number, I wouldn't get all of 0 to 3.
Right. So there's no finite subcover.
So there's no finite subcover of it. Intuitively, so I'm trying to give you the intuition that in the topologies we know and love, our sets that are going to be compact are going to be closed bounded sets.
Yes.
So in the real numbers, what that means is closed bounded intervals of the form like 0 to 3 like this.
Yes.
This would be compact. This one not.
Okay. Yeah, it seems like a really arbitrary thing to do right now. I don't see the point of it. I don't see why it's useful.
Oh, why compactness is useful?
Yes.
Well, I already gave you one, the extreme value theorem. That's a common application. Famous theorem from real analysis is called the sequential compactness theorem. Which, no reason you would know about that. Limits behave nicer in compact sets. That's one thing that they give us. Limits behave nice in compact sets. Yeah, I don't know what else to say. We'll see an example of it. The same way that you saw the intermediate value theorem for connectedness, we'll have a counterpart for compactness, the extreme value theorem. All right, but we'll end it there for today. We're now in the chapter on compactness. It's our last chapter.
Yay.
I'm guessing we have 3 classes left, and then we're done.
3?
Maybe.
Okay.
Maybe it will come out to 2. I should look at this. So we have compactness, maybe 2. So maybe 2 more classes, maybe 3 more. I'm not positive.
Cool.
I'll check on my previous lectures and see how long it took.
Is that gonna run through the entire textbook?
No. This is intended for 2 semesters of topology. So you'll notice we're getting right smack in the middle.
Oh.
But we can end that there.